All right, this is going to be part 1 of 2 of aerodynamics, specifically nozzle design. So like rocket nozzles and that sort of stuff. I think it's pretty neat, but it can be a little complicated. So let's start with a picture. So already I'm off to a great start with the picture. Cool. So this is a nozzle. That's it. Video ended. No, I'm kidding. So what do we know about a nozzle? So it takes combusted gases, sends it through the nozzle, and then it expands it and sends it out the exhaust. And the reason why it expands it, we'll get to it, but the reason why it expands it is because it increases the velocity, which is very backwards to think about, because like normally with fluids, to be honest, I still don't, well, I understand the math, but the concept I'm still not really grasping. Because you would think if you have this, like this, and you have V1, and then it shrinks down, and here you have V2, you would think that V2 is greater than V1. So why don't you just eject it right there? Why do you expand it? Because expanding it, you'd think that slows it down. But once you freaking break the sound barrier, it doesn't work that way, I guess. That's just what the math says. So let's define a couple things. So right at the choke, you have a Mach number equal to 1. Like that is choked flow, and you need choked flow for nozzles. So that's a definition. You can't have Mach equal to 5. You can't have it equal to 0.5. If it's less than 1, it'll be under, what would it be? It would be not choked. That's literally what it's called, not choked flow. It can't be greater than 1. And this concept of the Mach number has to equal 1 at the choke is applicable in a lot of different applications, not just nozzle design. But anyways, also, I'm going to refer to this part right here as like a star. We'll get to that a little later. So what do you have coming in? Well, you have super hot, super high pressure combusted gases. So that has a P stagnation, a T stagnation. It's terrible. Stagnation pressure and a stagnation temperature. Cool. How does that help? Well, there are a series of equations with this. There is a derivation, but no one really cares about it. These are the equations. Where's the best place to write it? I'll just do it here. P stag over P equals 1 plus K minus 1 over 2 m squared to the power K over K minus 1. So that's the first one. And for temperature, that's it. That is literally it. Okay, so what does this tell you? Well, if you know P stag, and you know that Mach 1, or that Mach is 1 at the choke, you can plug those two into here. You can plug in P stag, plug in the Mach. K depends on what fluid you're doing, but like everyone does air, so K equals 1.4 for air. And you can plug in K, and you can solve for P. So you can solve for the pressure right here, and technically it's P star if it's at the choke. So that's kind of how you use the equation. To backspace a lot. Okay. Same idea with temperature. You can get a T star right here as well. That's it. Now, why is any of this useful? Well, it's useful because you can calculate the thrust. For the thrust, you have to calculate it instead of at the choke. You have to calculate it, right at the end of the nozzle when it's fully expanded. So to do that, well, you're asking, what's the Mach number there? I don't know the Mach number. Well, you're not supposed to know the Mach number. You're supposed to know the ambient pressure. So if you're on the ground, like if you're, let's say that's a ground. This is a rocket. That's a rocket. That's the nozzle. If you're on the ground, P, call P amb for ambient is 101 kPa. But if you're up in space or as you go higher, the pressure decreases. Let's say it's like 10 kPa. So you know the pressure, like you'll have sensors on the rocket to measure pressure. Cool. So with that, you would plug in K, you'd plug in P stag, you'd plug in the pressure, and you'd solve for the Mach number. You could do the exact same thing with temperature, and solve for temperature, because you can plug in this Mach number into the temperature equation, and get the temperature. So now, with these equations, you can get, well, you know the pressure, and you can calculate the temperature of the exhaust. Now, why don't you just use T ambient? Because T ambient is like, let's say 80 degrees Fahrenheit. The exhaust temperature is like freaking thousands of degrees Fahrenheit probably. So you need to calculate the exhaust temperature using this. So again, from start to finish, you would start with the pressure equation. You would plug in P stag, you'd plug in K, you'd plug in the pressure, you'd solve for the Mach number. Then you plug the Mach number into here, and you plug in the T stag that you have, and you'd solve for the temperature. So now you have P ambient and temperature. I'm gonna just call it temperature. That's this temperature. So why is that important? It is important because you can solve for thrust, and you need thrust when you're like shooting a rocket into space. So how do you get thrust? Thrust is force equals m dot v. And to make sure the units work out, m dot is kilograms per second, and v is meters per second. And this would equal kilogram meters per second squared, which equals mass times acceleration. And mass times acceleration is force. So the units work out. So how do you get m dot? M dot is density times velocity times area. And that would be the area of the expanded part. So at the very end of the expansion. And velocity is just velocity. So you can rewrite it as p v squared a. Okay, well, how do you get the density? Density, I'll back up a step. So you have, what is it? You have that equation. I forgot what it's called, but you have it. And you could rearrange it and get M over V is pressure over R times temperature. And R is the gas constant. And for air, I erased the K, but it's, you can look it up. I think it's 287 for, like, if you're doing kPa, and it's 1717 if you're doing like feet or the other units. But yeah, you just literally look it up. It's a constant. But here we have the temperature, we have the pressure, so we can plug in the pressure, we can plug in the temperature, we can Google R. So we have all that stuff. Okay. And this is, I didn't finish it. M over V is density, mass over volume. So that's density. Now, how do we get, an area is just this. You literally know it because you freaking designed the nozzle. How do you get velocity? It's not as it's straightforward, but not in the way you think. So the velocity is the Mach number times the speed of sound, which makes sense. Because, and you know the Mach number, because you calculated it back here, and you plugged it into the temperature, so you know the Mach number. I'll just write it over here. You know pressure, and you know temperature, and you know Mach. So you know the Mach number. Now, what is the speed of sound? Well, it's not constant. It actually changes with temperature. So it is actually, rewrite it this way. Square root K R T. And this is the same R, and K is 1.4. Yeah. So now you can literally calculate it because you have V, you have density, you have area. That's all you need. So that's literally thrust. Okay, now, how do you know what size to make the nozzle? How do you know what area to need? Yeah, this part is a tiny bit more tricky, but it makes sense in a way. So, okay. What's the best way to explain it? Well, I guess I'll start by giving the equation. And that'll give me time to think, because it's a very big equation. So that's A over A star, and the A is this one. The A star is at the choke, the choked area. So typically that stays constant, and we change A. You could do it the other way around if you want. But yeah, it's just a ratio. Equals 1 over Mach number. Is it square? It's not square root. Yeah, it's a pretty beefy equation. I've tried solving it on like an online algebra solver thing, like Similab and a couple others, and they can't do it. It's like too much. If you plug in, well, okay, if you plug in the A ratio, like let's say that's given and you're asked to solve for the Mach number, it can't really do it. And I don't think it can do it the other way as well. There's just, I don't know, there's too many variables for it, I guess. But what are the variables? They're A star, M, and K. Cool. So I plotted this, as a, so I plotted the ratio as a function of Mach number. Yep, so as the Mach number increases, the area ratio freaking skyrockets, like literally skyrockets. I'll draw it over here. Because you can see I did y and then the Mach number is x. So this is saying as a Mach number increases, a over a star increases, which means if you keep a star the same, that a would have to increase. And that means, well, okay, so for a rocket, you start off with a high ambient pressure and you end up with a low ambient pressure. So if you plug that into this equation, you're gonna get a Mach number, M1 and M2. And that means you should end up with M2 being greater than M1 because the pressure P amb would be plugged into the denominator. I'll draw that specifically. Plug it into the denominator. And P stag you plug into the numerator. So yeah, you should end up with M2 is greater than M1. Regardless, the Mach number is changing. So how do you best fit that? So you have, let's say M1 is right here. That's, you're on the ground, and M2 is over here. M2 is over there. So that says that the area, well, it's not even on the plot because it expands so much. I could have just zoomed out, I guess, but that's fine. That's saying that your area of this part, that area needs to increase as the rocket goes higher in the air. And it actually does that, and it's pretty neat. And this is literally the function for it. This is literally the math for telling you exactly what area it needs to be. And it's not that complicated, like it's barely any equations. I think that's it, yeah. So the main equations are that, this one, and this one, and this one, and this one. Cool beans. Yeah, I think that's literally it. All right.